This video is produced by Sammy and
Kevin Burgess
for by Inquisition Press to support the workbook Sophomore Organic Chemistry 1 by Inquisition, available from www.byinquisition.org.
When chemists talk about SN2 reactions, they tend to say the nucleophile kicks out the leaving group. It's a sort of kicking motion. How do we decide if SN1 or SN2 is more likely? Well, if dissociation of a leaving group can give a carbocation that's very stabilized, then guess SN1. But if it's not very stabilized, guess SN2. If I take an optically pure alkyl bromide and displace with a good nucleophile like azide, will I get the same stereochemistry or opposite?
Opposite.
Opposite, because you get inversion. If we take this bromide, Sammy, will the product be an enantiomer or a diastereoisomer?
It would be a diastereomer.
Yeah, diastereomer of what we started with, via a trigonal bipyramid transition state. If we look at the reaction profile, do we get one hump or two?
One.
One. How many humps did we get for SN1?
Two.
Two. Are there any intermediates in SN2?
No.
How many intermediates in SN1?
One.
One. How many transition states in SN1?
Two.
Good. Now, alcohols are not good leaving groups. One way to make them a better leaving group is to put a mesylate or a tosylate on the alcohol. If we take an optically pure alcohol and tosylate it, it becomes a much better leaving group. If I take an alcohol and protonate it, and that alcohol can form a very stable carbocation, we will lose the stereochemical information. In other words, it will racemize. But if I take an alcohol and I mesylate it, the carbocation that could form not being very stable, I will get a
diastereomer.
That's right. It takes two chiral centers to form diastereomers, so this one here will give you
an enantiomer.
And the benzylic alcohol here will give you a
diastereomer.
And this one. This has one stereocenter that won't change, one that will be epimerized, and another one that will be cleanly inverted. It's impossible to do SN2 if we can't make the nucleophile approach in that orientation that gives us the inverted umbrella transition state. So we can for primary or secondary alkyl halides, but we cannot for aryl halides, cannot for adamantile halides. We can for benzylic and allylic, but we cannot for an aromatic. SN1 displacement involved reaction of the LUMO on the substrate with the nucleophile HOMO. In SN1, that LUMO is an empty p orbital. In SN2, it's the LUMO on the substrate that reacts with the nucleophile HOMO. And in SN2 reactions, the LUMO is the sigma star orbital, the empty orbital there. Remember the approach when considering which way a nucleophile could add to an iodocyclohexane. It's easier for the nucleophile to come in opposite the iodide if the iodide is axial than if the iodide is equatorial, because the nucleophile has to pass these hydrogens here. Here it describes displacement of bromide with cyanide and then hydrolysis to give acids. And once again, only chiral center adjacent to the leaving group is displaced. Phthalimide is a very good nucleophile to do SN2 reactions. After hydrolysis, the phthalal group is removed and we form phthalic acid. Phthalyl anion can do SN2 with inversion, and it's possible to make a variety of primary amines. Whereas if I took ammonia and tried to alkylate it, bad.
Bad.
Yeah, bad. Because it polyalkylates. And you get secondary and tertiary and quaternary ammonium salts.
Yeah, not very specific.
Not very selective. Very good.